Hi, physics. Mr. Janowski here. This is the first part of the chapter 37 slides. So, the way the rest of the year is going to work out, since there's only 3 weeks left, is we're going to start this chapter. I'm going to teach you some things. There will be a couple of homeworks, and then we're going to run out of time before we even get to the test. So, this is going to be it for physics 2. Just slides and a couple of homeworks, no test. So, seems a little weird, but what can we do? 2020, it's just a weird year. So let's get started with this stuff. So think back. Who discovered that a current moving through a wire creates a magnetic field? That would be Hans Christian Ørsted, which he discovered this quite by accident. Who was it that discovered that a changing magnetic field near a loop of wire caused a current? This is our old friend, Michael Faraday. And who put it all together? So this guy is one of the giants of physics. This is the one that people in the popular imagination just don't really know him as well, but he's really huge in physics. This would be James Clerk Maxwell. So yeah, Newton did all the mechanics, the classical physics. We kind of give him all the credit for that. Einstein did all of the relativity and some of the quantum mechanics. And then the guy who kind of put together all of electromagnetism and discovered that light is electromagnetic waves and all this stuff is James Clerk Maxwell, a Scottish physicist. So last chapter, what was the first right-hand rule that we learned? It was Ampere's right-hand grip rule. So if you have current flowing in the direction of your thumb, the magnetic field created by that current is going to loop around in the direction that your fingers do on your right hand. And what was the second right-hand rule we learned? This was the cross-product right-hand rule. So this has to do with moving charges or currents in a magnetic field and the force that you would get. So now we begin Chapter 37, Electromagnetic Induction. So yeah, Ørsted discovered, quite by accident, that a current moving through a wire created a magnetic field. Again, he just happened to move a current through a wire near a compass, and he saw that this caused the compass to deflect. So he was quite surprised, and this ended up being very important. But anyhow, the important idea is the current has to be moving, or, current is moving charge. The charge has to be moving. So a stationary charge does not create a magnetic field. And kind of the flip of this is what Faraday discovered, that a changing magnetic field near a loop of wire causes a current. A constant magnetic field near a wire does not cause a current, but a changing magnetic field does. So I'm giving Faraday credit for this. Faraday was not actually the first person to discover this. It was actually an American, Joseph Henry, shown here to the left. He discovered this before Faraday, but Faraday published his idea first, and Faraday did more work with this stuff, basically. So he researched this effect further. So, Joseph Henry did not get completely shut out because he got an SI unit named after him. The SI unit of inductance is named the Henry, after Joseph Henry's honor. So again, moving charges create a magnetic field and stationary charges do not. So yeah, Ørsted gets credit for that. So changing magnetic fields create voltages. And the first asterisk, voltages are also called electromotive forces, which is a bizarre name, or EMFs, and sometimes it's written as a script E. And the second thing is constant magnetic fields do not. And the double asterisk, this is mostly true. So go with this idea for now, and then a little later in the slides, we're going to see how it's not exactly true, it's mostly true. So, one thing we need to get under our belts is this idea, electromotive force, or EMF. So it's really voltage is all it is. But typically we tend to use voltage if we're talking about some kind of voltage source, like a battery or something like that. And we tend to call them EMFs if it is induced by changing magnetic fields. Not exactly changing magnetic fields. We'll get there. But anyhow, EMF, it's written different ways, often as a script E. It's voltage. It comes in volts. It is a scalar. So here's our old buddy, Volta. So back to Faraday. So Faraday's apparatus consisted of a battery, wires coiled around an iron core, and a switch. So that's the left side of this drawing here. So we have a battery. Wire coming out, goes around here, loops around this core. So this is going to make an electromagnet once this switch is closed, because then we'll have current flowing through. And yeah, this will make an electromagnet, which is going to, the magnetic field lines will go around here through this loop. Through this part of the core and through this loop. And this loop is all wrapped around, and it's connected to an ammeter, something that measures current. It's also called a galvanometer. Ammeter, it's one of the functions of a multimeter. It's an ammeter. It measures amps. So Faraday had hoped that if he ran a really big current through this loop, this would somehow cause a current to be created over here. And so he set this all up and he did it, and he was kind of disappointed because he wasn't creating a current on this right side of this, no matter how big this current was, until he discovered something. So what he discovered is that right after he threw the switch, then he did get a current over here on the right side. And then the current would quickly fade away. And then when he opened the switch again and the current stopped flowing over here, he would briefly get a current over here on the right side in the opposite direction from the first one. And what he concluded from this is that a changing magnetic field induces an EMF, an electromotive force, a voltage, but a constant magnetic field does not induce an EMF. So, yeah, the instant he closes the switch, current starts to flow, and we start to get a changing magnetic field through this core. And that changing field creates this. And then after the switch has been closed for a while and the current's just flowing, now we have a constant magnetic field that doesn't induce a current. So, yeah, the changing thing is the key. So Faraday went further with this. So this time the magnetic field is not going to be changing. So what we've got here in this apparatus is a battery over here connected to a solenoid. So this solenoid is going to become an electromagnet. And then we have another solenoid down here with a bigger, diameter in the middle. And this solenoid is connected to a galvanometer, an ammeter. This thing's going to measure current. So what he discovered is, connect this. So now this thing is an electromagnet. It's got a magnetic field. When he moves this, into this core, as he's moving it, he starts to get a current through here. And then if he just holds it there, nothing. And then if he quickly removes it, he starts to get a current again, this time in the opposite direction of the first one. So the thing is, the magnetic field being created by this solenoid is constant, but something else is happening. This magnetic field is moving near these coils of wire. So it's the relative motion that causes the current. So going with this, which, this picture doesn't exactly show this, it's not this magnet that needs to move is basically the point of this slide. So if you were to hold this magnet in place and then move this other one near here, that would also create a current. So it's the relative motion of the loop and the magnetic field is the other way to do it. You can do this with no motion, and which is what this one did. The current, the charges were moving in the current, but the loops weren't moving, the core wasn't moving, none of that was moving. Or you can have a constant magnetic field and move that near the loop of wire, or move the loop of wire near the constant magnetic field. So yeah, we've induced an EMF, which is a voltage. So we need to get this idea, magnetic flux. So that letter there is a capital Greek letter, phi. That's a phi. It looks like a theta on its side, but it's a phi. So phi sub B, B for magnetic field. So consider a flat loop of wire of any shape with an area A. So this loop happens to be a circle. Could be a rectangle, could be any shape. Just something that's got an area, capital A. And now consider an imaginary line perpendicular, normal to that area. So our loops are going to be flat like this. And, this loop describes a surface, and so you draw perpendicular to that surface. And now we're going to have a constant magnetic field going through that area. So we need to consider the angle between our magnetic field, shown by the red lines here, and that imaginary line, this perpendicular we drew, which is also, it's called a normal. Normal meaning perpendicular. So area A, magnetic field B, and angle theta between the line perpendicular to the area and the magnetic field. So what magnetic flux is, phi sub B, is equal to B, This is the strength of the magnetic field, and we're just going to have constant magnetic fields. The area of the loop and cosine of theta, that angle there. So this is magnetic flux. So magnetic flux, I tried to look up the exact right way to pronounce this. I believe it's actually Weber in English. That to me looks like it should be Weber. In German, it would be Weber, but yeah, I think these are called Webers. I like Weber. I mean, Weber should have two B's, but whatever. Anyhow, we have a new quantity, magnetic flux. Its symbol is phi sub b. Its unit is the Weber, and a Weber is a Tesla times meter squared, and a Weber is a scalar. So, yeah, there's your formula for magnetic flux and what all the things mean. So, what Faraday discovered, it's not that the magnetic field needs to change per se, although that is definitely one way to do it. It's the magnetic flux that needs to change. A magnetic flux that changes will induce a current. So here's a loop, but imagine this loop goes around and around and around like a solenoid. So let's say our loop has n turns. The resulting EMF, voltage, symbolized by this script E, is going to be given by E is equal to minus n, the number of turns in your loop, times the change in your magnetic flux over the change in time. So this is Faraday's law of induction. And if you're taking the calculus, you can probably imagine what the differential version of this would look like. But this is an algebra-based physics 2 class, so I'm going with deltas instead of D. So if we're looking at this, the minus sign is very important. So the minus sign tells us that the current produced by the induced EMF, so this changing flux is going to cause a current. It's going to induce an EMF, which is a voltage, which is causing a current, and the direction of the current that is induced is going to create a magnetic field that opposes the change in flux. So yeah, that's a complicated idea. I've got slides where we'll look at this idea. So this is known as Lenz's law. So Lenz's law and Faraday's law kind of go hand in hand. Lenz's law determines the direction of the induced current. So right away, let me point this out. There's going to be two magnetic fields that we need to be aware of when we're doing these problems. One is the one that's already there. So in this drawing, these red lines are giving us the existing magnetic field. So I don't know what to call it the existing one. The change in the flux is going to induce an EMF that's going to cause a current that's going to cause another magnetic field. So yeah, we have kind of the existing one, and we have the one that is going to be created by the induced current. So in order to produce an induced current or an induced EMF, I'm kind of using them interchangeably. If you have a voltage through a conducting wire, you're going to get a current. So they really go hand in hand. So to produce an induced current, you need a closed conducting loop. You need an external magnetic field. So this is the one that's existing there. I'm sorry, I said field. You need an external magnetic flux through the loop that's going to change with time. So it needs to be varying. So the first thing you're going to do is determine which way the magnetic field is pointing. So in this case, our magnetic field is pointing up and to the left. Then you need to determine, this is really the important thing, whether the flux through your loop is increasing or decreasing. Because this is where Lenz's law is going to tell you which way the current's going to go. So if the flux is increasing somehow, the magnetic field due to the induced current is going to oppose the existing magnetic field. So what does that mean? If the magnetic field, this existing one, starts getting stronger, then the flux through this loop is going to increase, which means we need the magnetic field from the induced current to go the other way from this one. Hopefully that makes sense. So yeah, if we start getting more lines here, so the existing field starts getting stronger, is one way this could happen. We need the magnetic field created by the current that's going through this to go the other way. So which way would that go? It would need to go down. So I actually looped it the wrong way. So it would need to go this way. Oop. It would go that way. On the flip, if the flux is decreasing, the magnetic field due to the induced current will go with the existing magnetic field. So if this field starts getting weaker, so we're losing flux, the induced current is going to create more flux, is how you can think of it. So yeah, if this existing field gets weaker, we need the current created by this we need the magnetic field created by the current that is induced to give us more flux. So which way would that go? Think of your Ampere's grip rule. It would go this way. This would, if the current's going around like this, it would produce more magnetic field through here and give us more flux. So yeah, the last part of this is you have to use Ampere's right-hand grip rule to determine which way the induced current must flow to create the necessary magnetic field. So I'm imagining if you're hearing all this for the first time, it sounds very complicated. Fortunately, I have slides. So we'll go through a couple of examples where we do this. So what's going on in this picture here is we have a magnetic field. So a magnetic field is in kind of this area right here, and importantly, it stops. The magnetic field is constant through this area, and then there's no magnetic field over here to the right. So the first thing we need to do is determine which way the magnetic field is pointing. So we're looking at the tips of the arrows, so the magnetic field must be coming towards us. The magnetic field is coming out of the page. So the next thing we need to determine is whether the flux, phi sub b is equal to BA cosine theta, is increasing or decreasing. So while that loop is in the magnetic field, it's got a constant flux because it has a constant area and the magnetic field is throughout the entire area. Once this guy gets to the edge of this magnetic field and keeps moving, it's got less flux because the magnetic field isn't going through the whole area. So in this case, our magnetic flux would be decreasing. So yeah, we're losing flux. So what we need is the current that is induced needs to travel in the direction that would increase the flux, because the motion of this loop out of this magnetic field is going to lose flux. So we need to have a current that increases the flux. So which way would that be? That would be counterclockwise. So you have to use the grip rule and determine if the current's going this way, that's going to cause more magnetic field through this area, which is what we want because the motion of this loop is losing flux. So we need to increase the magnetic field so that we keep getting more flux. So another example. This time we have a big loop like this, and something is going to cause this loop to shrink. So maybe this loop is made of coils, and the coils are all going to shrink. So the first thing we have to do is determine which way the magnetic field is pointing. So the magnetic field is pointing into the page in this case. We're looking at the tail feathers of these arrows. So now we need to determine whether the flux is increasing or decreasing. Well, look at your formula for flux. In this case, B is the same and the angle is not changing, but the area is getting smaller. So that means the flux is decreasing. So we have to use Ampere's right-hand rule to determine which way the induced current must flow to create the necessary magnetic field. So we need more magnetic field going into the page. So which way is that going to be? That is going to be clockwise. So look at that picture. Hold out your right hand, do Ampere's right-hand grip rule, and convince yourself that if the current flows clockwise through this loop, that's going to create more magnetic field into the page, which is going to help make up for the magnetic flux that we're losing. So another example. So this time we have a loop, and the loop is just sitting there. There's no magnetic field, but we're going to take a bar magnet, and we're going to direct it through the center of this loop. So right now, if you can tell from my wonderful 3D drawing here, the magnet hasn't yet reached the plane of the loop. So as this is coming towards us, we need to determine which way the magnetic field is pointing. So imagine the magnetic field from this guy. You would have the positive lines going out from the north end, looping around, coming back to the south end. So the magnetic field here is kind of going into the page. So as this magnet moves towards this loop, is the flux going to increase or decrease? It's going to increase as this guy gets closer and closer here. So magnetic field into the page, our flux is increasing. So now part 3, we need to use the grip rule to determine which way the induced current must flow to create the necessary magnetic field. Well, we're getting more flux by moving this magnet into this loop, which means we need to get a current that causes a magnetic field pointing out of the page. So in this case, the magnetic field is going to go counterclockwise. So yeah, use your grip rule. Convince yourself that if the current's going this way, it's easiest to see right here. If the current's going up through this point your thumb up along the right-hand side of this loop. That's going to cause a magnetic field in the middle coming out of the page. So that's going to help make up for the fact that we're gaining flux going into the page. The magnetic field coming out of the page from the induced current is going to counteract that. And finally, the last one. So this time, we've got this loop here, and the loop is in the plane of the page, but the loop is going to start to rotate this way, which means this side, the left side of the loop, 9 o'clock, is going to start to come towards us, and the right side of the loop, 3 o'clock, is going to start to go away from us. So that's what I've tried to indicate here. Hopefully that makes sense, my little drawing there. So yeah, first thing, determine which way the magnetic field is pointing. Well, look at your arrows. It's going to the left. Is our flux going to be increasing or decreasing? Well, currently our flux is actually 0 because B is something, A is something, but the angle between them, the angle between the normal, so the perpendicular from our loop, and our magnetic field is going to be 90 degrees. Cosine of 90 degrees is 0. So currently we have 0 flux. As this thing starts to rotate towards us, it's going to start showing it's going to be showing its area to the magnetic field. So we're going to start gaining magnetic flux to the left, which means our induced current must create a magnetic field through that area that's going to the right. So which way is going to do that? This would also be counterclockwise. So convince yourself that as this loop starts to spin around like that, if we have a current going this way, down like that, and it'll be easier to see up like here because it's easier to hold your right hand this way, that's going to cause magnetic field going to the right, which is what we need here. So I realize this might be confusing. We'll see. So to review quickly, because I'm sure this video is getting kind of long, what are our units of EMF? EMF is just voltage. It's a different way of saying voltage. We use it in this context. If you're inducing a current, you kind of talk about the EMF that is induced, not the voltage, but it's voltage. Different symbols. Sometimes it's a script E, sometimes it is a V. Sometimes you write EMF, which again, this is a terrible name. It's not a force at all. It doesn't have units of newtons. It's got units of volts. But yeah, EMF is voltage, basically. And yeah, I said that you need a changing magnetic field to induce a current, which is kind of correct, but it's not exactly correct. What actually needs to change to induce a current? Well, what needs to change is the magnetic flux. So yes, you can get a current by changing your magnetic field, but really the important thing that needs to change is the flux, which is given by this formula here. So it's not just magnetic field B, it's B times A times the cosine of theta, where theta is the angle between this normal to the area, this dotted line, and the magnetic field. So we learned a new Greek letter today. Hopefully you guys are finding this interesting.